Yeah, good morning, class. In the last lecture, we have seen some aspects of designing a learning system, right? Now let us proceed with that and let us see how to arrive at a final design. Can you see the presentation?
Yes, ma'am.
Okay. Okay, in the last session, we have seen how to design a learning system by choosing the training experience in the beginning as the first criteria and then choosing the target function, right? And also we have gone through concepts of choosing a representation for the target function and choosing a function approximation algorithm. Okay, now I'm just going to recap these two topics once again because they are a little complex to understand. I'll try to give you more and more examples on that so it will be easy for you to take up that particular essence in that topic. Okay. Now we have chosen a representation for the target function in order to represent how the next move should be for a checkers pawn from its current legal state, right? So we are dealing with the problem of designing a computer program that can play checkers or chess with itself or with a human champion. Okay, so our task here is to play the checkers game. That is, the machine should play the checkers game, and the performance we measure is how many games it will win against its opponent, and the training experience we provided is the recorded board states or with direct feedback or indirect feedback. Okay, now for that we have specified ideal target function V. Now I told you what is this ideal target function. For every machine learning task, we can't simply give it instructions in the form of human language, right? So we need to give it some instructions in the form of mathematical expressions. Okay, we can't ask it to simply generate all the prime numbers, right? We give it some instructions. We mathematically model the problem so that it can do that task in a meaningful way, right? So and nowadays even natural language processing machines are coming which can understand normal language, convert it into a machine learning task and do the give some good performance, right? But in order to start learning about the basics of any machine learning task, let us see that a machine can't understand what instructions we give in natural language or some high level language. So we are trying to model it in the form of mathematics and write some instructions to the machine in order to make it understand how to execute a particular task. Now here the task is playing chess or playing checkers, right? So we have chosen a target, we have chosen a representation that the learning program will use to describe the function we had that it will learn. Okay, now can any one of you tell me what is the difference between V and V hat? I assume that you understood very well in the last class what I explained you about the ideal target function and the estimation we had. Ideal target function is V and estimation of that ideal target function is V hat. So what is the difference between these two? Students? Students? See, school children, for them, if we take online classes, we can't stop them talking, you know. They respond very well. Class teachers find it too tough to stop them talking during the class. They keep on answering questions very enthusiastically. And they ask a lot of doubts also. Why not you? What is the difference between ideal target function V and the estimation V hat? Not even one of you can answer this. Or everybody logged in and you're sleeping. Speak out.
We had test estimation.
Okay.
V is ideal function to be met, but we can't actually.
Very good, exactly. Ideal target function is some representation which tells us that it can make 100% prediction, correct predictions. Okay, but in the general sense or in the real time, we can't make 100% prediction, accurate predictions, right? Prediction itself says that some assumption is involved in it, some guess is involved in that. Means you're trying to estimate something, but you're not trying to tell that particular thing with 100% accuracy, right? So the target function we try to design is to achieve 100% accuracy. Okay, but we always tend to go towards that but never meet it, right? So this V hat is called as the estimation of that target function V. This estimation we try to refine each time iteratively so that we can increase the accuracy. We can't completely meet 100% accuracy, but we can try to increase the accuracy, right? The machine each time it learns from its previous games in this case, and it tries to improve its accuracy of playing the game in order to win the game. Did you understand? Who is that who answered now?
Ma'am Apurva, USN 06.
Okay. Did you get this point now? Now there are lots of options like creating the tables of the distinct board states or collecting the rules from which board state to which board state it can go, multiple board states it can go. All these are various options available. So whenever you're writing or deciding this target function, we should be very expressive in the representation. Means it should cover many instances. It should cover many scenarios. If you write a target function, it should be generalizable. What do I mean by generalizable? It should apply to different examples. It should apply to different possible board states, right? This is called as expressive representation, generalizable representation. Now, when you are generalizing a target function, in order to be more expressive, then you need lots of training examples, correct? Now, you're teaching a child to play the chess and he is encountering lots of challenges from the opponent player. Okay, now the child can face all those challenges only if he receives lot of training from an expert coach, correct? That is how you need to understand this trade-off to be maintained. What trade-off you have to maintain in designing a learning problem is you have to find out a target function which should be very much representative, and to achieve that you need lots of training examples. Did you understand now how to choose a target function? It should be generalizable, and in order to make it more generalizable, you need lots of training examples. You need to provide it lots of training. Now for that we have taken a simple representation. Actually this doesn't cover all the instances, but we are taking the simplest representation in order to understand how to arrive at a final design. But remember, these steps that we followed in order to arrive at a final design is not final. You can do it in several different ways, but we are taking the simplest methodology in order to start off, in order to make a beginner understand what exactly are the steps involved in order to design a good learning system, right? Now we have taken different board states x1, x2, x3, x4, x5 and x6. Means in order to move upon from this particular state forward in any of these directions, you have to consider all these board states, right? How many black pawns are there? How many white pawns are there? How many black pawns are threatened by the white pawns? Means if it moves in a certain direction, it may be conquered, it may be killed by the opposite pawn, right? So how many pawns are threatened on either side? That you have to consider. And how many kings and queens are there on either side, on black side and the white side? All these you are considering in order to move a pawn from a legal board state to another legal board state. And our objective is to optimize that move. Understand clearly. We are trying to move upon from one board state to another board state. Okay, now that move is our target function. Now, what is the objective behind achieving that target function? Is to find the optimal move, to find the best move, so that it goes towards winning the game. It proceeds towards winning the game. Did you get the point now? Now, for every such move, for every target function specifies the move to a next board state, right? Now, for every such target function, how we are representing a linear equation? As function as a linear equation of W0 plus W1x1 plus W2x2 and so on up to W6x6. Why? Because you are considering 6 board states. Means you have the number of parameters here is 6. Now, when I take a patient data in order to confirm whether he is a COVID positive or not, what are the parameters I take? His breathing level, his oxygen level, his coughing, running nose, yes or no, all these are parameters. In this case, the parameters are the board states, individual board states, right from X1 to X6. Now you are assigning weight to it. What do you mean by this weight? It has learned from the previous sequence of moves, from the previous games, that this board state should be given this much importance, that is W1. This board state should be given this much lesser importance, that is board state W2. Right? Like that, it gives some quotient to each of the parameters by learning from the previous experience. Okay, now I should give more importance to the pawns that are threatened rather than the pawns, rather than the total number of black pawns on the board. Understand this, I'm repeating again. Now, when I am making my next move, or when the machine is making the next move, it should give more importance to the threatened pawns rather than giving importance to number of pawns on the board. Means I'm trying to give more importance to X5 by giving more weight to W5 rather than giving more weight to X1, that is through W1. This is how you need to understand the weights assigned to each of the parameters. Now, what is this W0? This also I have explained in the previous session. Can anybody tell me what is this W0?
Ma'am, it's error, ma'am. Error weight.
Very good. Who is this?
Apurva, ma'am.
Again, Apurva. Very good, Apurva. You're focusing very well. W0 is the error. Remember, this target function is not accurate function. It's a prediction. It is making predictions, trying to achieve 100% accuracy, but it is on the way and it will be on the way. It can't always make 100% predictions because it depends on the opponent's play also. It depends on the opponent's game also. What moves he take, this machine can't predict, right? Up to some extent it can predict, but not completely. So it can't always win the game. Sometimes it loses the game. So these moves are just the estimations in order to win the game. Now for that estimation, we are giving this linear equation. For every move, this entire equation will be taken into consideration. And whatever value it gives, based on that, it will start moving to the next board state. Now we have arrived at a partial design of the Checkers learning program by giving the task. You know now very well what is the task, what is the performance measure, and what training experience you provide to excel at this task T, which is measured in terms of performance P. You understood? I'm repeating again. In order to excel at a task T for any machine, to give good performance P, we have to provide it with sufficient training E. Now, we also understood how a target function have to be formulated. In this case, what is a target function? What task has to be performed? What function has to be performed by the machine each time to move to the next board state, right? So the move V is defined as moving from any legal board state B to next board state by considering for each board state some value in the form of real numbers. Wherever the value is more, it tends to move in that direction. It wants to move in that direction so that that move may be optimal in order to win the game. Okay. Now, what is the target function representation overall? From the understanding we have derived so far, V is the ideal target function, and estimation of that target function is this one by considering 6 board states and associating some error with it, so that you say that you're not estimating it with 100% accuracy. There is always some error associated. There is always some prediction error associated. So your task is to minimize this error. Got it? Now, choosing a function approximation algorithm. How to choose a function approximation algorithm in this case? We have chosen the target function representation, and we are now trying to choose a function approximation algorithm which will reduce that error W naught, which reduces the prediction error. Okay. Now I have student data. I'll give you a simplest example. Focus on this so that you can understand this checkers example. Okay, I have student data, and that student is spending these many hours of time. Time is taken on the x-axis and marks obtained by him. You're trying to model this particular problem. You want to know, given the time spent in studying, you want to predict how many marks he can achieve. Or rather than marks, we can take it as percentage. That will be a more general term. Okay? I'm repeating the problem again. If you have the data of students' time spent on studying, you can predict what percentage he can achieve in the exams. Means you're trying to predict his performance, right? Now you have some data. A student spent some 2 hours of time, so he got less percentage. Now a student spent more time, he got higher percentage. A student spent maximum time in studying, so he achieved good percentage, right? Now I'm trying to fit a line to this. I'm trying to find out an algorithm in order to explain the behavior of these students, old students, so that based on the behavior of these old students, or based on the time spent on the based on the time spent in studying by the old students and what percentage they acquired, I'm trying to guess or estimate what would be the percentage achieved by a student if this much is the time spent. Say a new student spent 6 hours in studying. Now I want to predict how much percentage he can achieve. For that, what is my target function now? Can anybody tell me what is the target function now? The student percentage can be taken as y because you are trying to predict. This is a dependent variable. Percentage is a dependent variable. Now this dependent variable is being predicted with the help of independent variable time, that is x. Got it? Now we are giving it as w0 plus w1x. Now what is the parameter here? In checkers game, the parameters are x1 to x6. In this case, the parameter is just one parameter we have. To take the problem as simple as possible, we have one parameter, that is time. So whenever whenever the machine is given the time spent in studying by a student, immediately it should be able to predict the percentage that can be obtained by him in the exams. Okay, this is my target function. And this function should explain as good as possible even the new students data also, even the new students behavior also. Means if I tell that the student spent 8 hours per day in studying, means X is given, then it should be able to predict what percentage he may achieve in the exams, right? So I am trying to make this function ideal. I am trying to make this function accurate enough to make this prediction as correct as possible. But there will be always some error associated with it, that is W naught. Now I want to minimize this. I want to minimize this error in prediction so that my entire target function will go towards accuracy, 100% accuracy. Got it? So I'm trying to fit a line now. This line is nothing but y equal to W naught plus W1x. I'm trying to explain the behavior of all these students in a general equation. That is y equal to W naught plus W1x. Right? Now this equation is represented by a line fitting these training examples. Got it? Now on this line, whatever you make are the predictions by using this equation. Now away from this line are the actual examples. Now the difference between these actual examples and this predictions made is W naught. That is your error, prediction error. Did you get this point clearly? The difference between this line is my ideal target function. Now I wish that all the predictions should be, all the training examples should fit along this line. But that is not the real case, right? In real time, I can't make 100% prediction. So there would be some training examples away from this line. Some may be on this line, some away from this line. Now the difference between this ideal functions data point means if I make 100% accurate prediction, my training example will be on this. But because there is some error, my training example is here. Now the difference between these two is called the error in prediction. That is W naught. Now did you understand this target function in the previous case? This function, I explained it with respect to students studying time. Now there you have only one parameter, time. Here you have 6 parameters, 6 board states and error associated with that. Did you understand, students? Now how to choose a function approximation algorithm. For this, in order to decide this linear equation y equal to W naught plus W1x in the simplest case, in order to design this equation, you have to approach some algorithm, right? For that, we have an algorithm called as LMS or least mean squares. Remember, we are now trying to represent this or solve this particular problem of fitting the data by using LMS, least mean squares. Least mean squares means the squares of these errors of all the training examples have to be minimized, has to be the least. That is why we call it as least mean squares. In the last class, I have told you, right, sum squared errors. That sum squared error should be the minimum in order to get the best fit of this line. Means you're trying to design a target function which will minimize all the squares of the errors. Got it? In order to learn the target function, we require a set of training examples, each describing a specific board state B and the training value V train of B. Now, this is the training value and this is what would be the value for the next move. Now what training you are providing for this particular board state? What are other board states? X1 equal to 3, number of black pawns, number of white pawns equal to 0. And other categories are also given some values. Now because number of white pawns are 0, it is the winning state for black pawns. Because it has 1, we can give it a weight plus 100. Right. That is how you assign value to a particular board state. Now let us describe a procedure that first derives such training examples from the indirect training experience available to the learner, then adjust the weights to best fit the training examples. Initially, to start with, it will derive its experience from the previous game moves, from the previous sequence of moves. Okay, it has assigned some weights. Now, are these weights final? No. It has to keep refining those weights in order to reduce the prediction error. Means in order to refine its move to the next state as correct as possible, as optimal as possible. Means all these weights will be kept, they'll be kept adjusting again and again by learning from its previous games. Correct? A child is playing a chess game. Now it has made some decisions about the movements. Now that is very naive, right? In the initial stage, he may not know the best moves, but he'll make some moves. But later, as he learns by playing against himself or by playing against a by playing against a coach, he will try to refine his moves to get the best moves in order to win the game, right? Means he is trying to refine his game. Here it is trying to refine its weights in order to decide the next best move. Got it? Now for estimating these training values, what has to be done? According to our formulation of the learning problem, the only training information available to our learner is whether the game was eventually won or lost. Let us keep it again very simple. Now the training example available to the learner here is the game is won or lost. For the sequence of moves, game is won. For another sequence of moves, game is lost. Only that information he has. Now on the other hand, we require training examples that assign specific scores to specific board states. Okay, so it will assign scores to specific board states based on whether it has won the game or lost. Now, easy to assign value to board state that correspond to the end of the game. End of the game, say I have given this example, but again and again I'm repeating in order to make you understand. This is the last state. Now, if it makes a move in this direction, it will win the game. So what type of value you assign for this particular move? You assign it as 100. Why? Because you know surely that the game is won. So you give it plus 100. And if the game is lost, you give it minus 100. If the game is drawn, you give it 0. But what about the intermediate stages? This pawn might have moved in this direction, and in this direction. Now, what weights do you assign to this move, and this move? That is a difficult task, right? Difficult to assign training values to the numerous intermediate board states. Now, in spite of this confusion, we can take it as one simple approach. That is to assign the training value of V train B for any intermediate board state B to be V hat successor of B. Means, if you take a board state like this, for this, what weight it has to be assigned? Whatever is the estimation that is drawn from the linear equation we have done in the previous case, the target function, right? This will take help of the target function in order to assign a value for this move. Okay, so it has moved from a state B to B dash, or here it is represented as successor of B. Now, what value do you assign to that move? That is V hat. That is your combination of all the parameters. Means you have to take into consideration x1, x2, x3, x4, x5 and x6. along with their quotients, that is weights, means their importances, to be considered in order to move from this board state to this board state. Okay, that value will be calculated 12 or 20 or 34. That moves value will be calculated by substituting in that equation x1, x2 and so on up to x6. Got it? So we are representing it as V train B is nothing but how it derives the training example is by substituting that target function and moving on to the next state, that is successor of B. Right? So how we can represent that rule? Now we had successor of B means the move to next state is learned by the training you provide to that current board state, V train of B. Got it? Now V hat tends to be more accurate for board states closer to game's end. We can easily assign that. But for intermediate board states, it is difficult. That is what I told you. Under certain conditions, the approach of iteratively estimating training values based on estimates of successor state values can be proven to converge towards perfect estimates of V train. Understand this carefully. Initially, you give it some weights, but later that weights have to be refined. Got it? Initially, you give some weights W0, W1, W2 and so on. Okay, initially you give some weights to those the W1, W2 and so on. Now you keep on refining them. You keep on refining them in order to minimize the prediction error so that finally they converge. Means you can't make any more predictions, any more accurate predictions than that. Okay, so the predictions state is not refining anymore. In that case, that is your final weights for that equation. Got it? So the weights will converge. Converge means no longer change. Though the machine learns from its previous training examples, it no longer changes. That is called the point of convergence. It is converging. It can't be refined anymore. It learned to its maximum state possible. Right? That is called as the final state, where you can say that this is the target function that is optimal. Not completely ideal, but optimal. Now, how to adjust these weights? Now, we have to specify the learning algorithm for choosing the weights Wi to best fit the set of training examples B and V train of B. Means for every board state, what training you provide for that board state in order to go to the next board state. Now, one approach is to define the best hypothesis or set of weights. In this case, our hypothesis is to arrive at set of weights which will make correct predictions, which will make almost correct predictions, as that which minimizes the squared error E between the training values and the values predicted by hypothesis we had. Okay, now how do you define this hypothesis? Your hypothesis is to reduce the prediction error, simply the prediction error. This is the move that is suggested by the training examples learned by the machine, and the target function will suggest this move, that is the prediction of the next move. Now, if both are same, there is no error in the prediction. But always this is an estimation, there will be some error associated in the prediction. Now you have to minimize this error. You have to reduce this prediction error. You have to keep this value as less as possible. Okay, so this E has to be minimized. That is why I call it as sum squared error, because you are summing up. Sigma stands for summation, right? So you are trying to add up all the errors in the predictions, whether they are negative or positive. Sometimes it may be forward than the prediction. I gave you the example of weather forecast. Today's weather is 34 degrees, but it has been predicted as 33.8 degrees. So the prediction error is minus 2 degrees. Now minus 0.2 degrees. Okay. Now today's weather is 34 and it has been predicted as 35. In that case, the prediction error is plus 1 degrees, right? Now this error has to be minimized. Why you're squaring is just to remove the negative sign. Error is an error, positive or negative, right? So you're squaring it in order to remove that negative sign. Now that sum of all the errors with all the training examples predictions have to be lessened, minimized as much as possible in order to arrive at an ideal target function. In order to arrive at a target function that would make better and better predictions. Now, as you go on refining it, as you go on making better and better predictions, weights have to be adjusted. Correct? If weights can't be adjusted, performance can't be improved. Now, minimizing the sum of squared errors, very important for this least mean squares. The algorithm we are taking here is least mean squares. Least mean squares means the sum of squares should be the least, minimum. Now, minimizing the sum of squared errors is equivalent to finding the most probable hypothesis given the observed training data. Okay, so you're trying to find the most probable hypothesis, means you're trying to find out the ideal weights in order to make correct predictions, in order to minimize the error in the predictions. Now we require an algorithm that will incrementally refine the weights as new training examples become available, and that will be robust to errors in these estimated training examples or training values. Got it? Now what all I explained so far is put into this statement. We now require an algorithm, in this case least mean squares, that will incrementally refine the weights, means it will start adjusting its weights as new training examples become available by learning from its training examples, and that will be robust to errors, means you are trying to minimize the errors in these estimated training values. Okay, so the child or the machine is trying to learn from previous experience, and it is becoming more and more robust to errors. It will not make errors in its moves any longer, because it is learning again and again, it is learning again and again, it is learning iteratively. Got it? Now least mean squares or LMS training rule is suitable in this case because you are trying to minimize the sum squared errors. Now for each observed training example, it adjusts the weights a small amount. It adjusts the weights in a small amount in the direction that reduces the error on this training example. See how beautifully this text is given by the author. For each observed training example, now what it is trying to learn from that, it adjusts the weights a small amount. It is trying to adjust its weights a small amount in the direction. What is its objective to adjust the weight? To reduce the error in prediction, to reduce the error on this training example. Okay, this is nothing but an approach called as stochastic gradient descent search through the space of possible hypotheses. Here our hypothesis is to adjust the weights. Now whenever see, before explaining what is this stochastic gradient descent, students, I am asserting on this point again and again. Remember, you can't understand all these terminologies in the first instance. Replay these videos again and again. First time you will have a basic idea, second time you will start understanding, and third time no one can help you or stop you from understanding. Nobody can stop you from understanding, because these are mathematical terms and most of the students are not comfortable with these terms. Simply, if you're not understanding it in the first instance, don't leave it. Listen to it for the second time and third time. You'll surely understand. That is what I have done. When I started learning about this machine learning concepts, initially it was like a alien subject for me. I didn't understand anything, and I'm not at all comfortable in my college days with probability and statistics. But I repeatedly saw the videos. I repeatedly read the blogs about these mathematical and statistical usages of these terms. Little hard work have to be put. If you just put that hard work and focus, third or fourth time, you'll surely understand what are these underlying concepts. And once you understand these underlying concepts, you will become a machine learning expert. Why? Because you know all the intricacies behind these advanced concepts. Nobody can stop you from becoming a machine learning expert. But if you want to excel in data science, you have to understand the mathematical concepts behind. Okay, and these concepts are not advanced statistics also. All the basic things what you have learned in your school days. Only that being applied in different scenarios. That's all. Okay, so do not lose hope. These will seem to be complex in the first instance. Then after understanding in the third or fourth try, you will think that, are these silly concepts I didn't understand in the beginning? Are this really this complex? What I thought? No, you will surely understand this. But only thing is repeated reading of the concepts. Okay, I don't tell that this subject is easy. It is hard if you do it for the first time. It is little hard, little less harder if you do it for the second time. Third time it will be very simple for you, I promise. Okay, so you have to focus a lot. Repeated hard work is required in this. Okay, how the machine understands iteratively, in the same way student also have to understand iteratively. In the initial stage you don't understand anything, but in the final stage it will look very easy for you. Now let us go to this stochastic gradient descent. It is something like, I'll put it in very simple terms. Say there is a mountain, a small story for you. There is a mountain. Now you're trying to descend the mountain. Descend the mountain means come downwards to the foothills. Okay, somewhere this position. You are starting from here. You are here. You want to come down. Your objective is to reach this position, minimum position, that is the foothill of this mountain. Now, you don't know which way you have to go down. Now, what is your approach here? You just search around this direction, and this direction. Now, in order to go downwards, you should find the steepest direction. Steepest means where the descent is very steep in this direction, right? Now, you're going in a different way. There is no maximum steepness. So if you go in that direction, it will be late for you to reach the foothills. So you go in this direction? No. You go in this direction? Yes. The steepness is more in that particular direction. So if you move in that direction, you may reach the down part of the hill easily. Okay. So that is your optimal move in that particular position. Means that is your local minimum. Locally, what is your knowledge? To move in this direction in order to reach towards the foothills. Now you reached again here. Again, you have different options. This direction, this direction, this direction, and this direction. In this direction, it is your local minimum. Means the steepness is more. And locally, if you move in that direction only, you can little proceed towards your goal. Okay. Now you proceed in that direction by taking little steps. Means you're learning. Initially, you'll take larger steps. But as you come to the bottom part, you will tend to take smaller steps, because if you take larger steps, you may go in a different direction. You may deviate in a different direction. That is why you're taking smaller steps as you go on to the foot part of the mountain. Right? Now your learning rate initially is more because you have more options. But as you go towards the bottom of the hill, your learning rate will reduce because you have gained some experience. So you will better know in what way you can proceed. So your learning rate will start coming down, and finally you'll reach the foot part of the hill. You'll reach the bottom of the hill. What you're doing is, at every stage, you're trying to move little further by assessing your best move, by assessing your optimal move. Okay, this is called as stochastic gradient descent. Now, why you call it as stochastic? What is the difference between stochastic and deterministic? Very simple. These terms actually look like tongue twisters, but they are very simple. Stochastic is random process. Say, if you roll a die, can you tell with 100% confidence that 6 will come on the top or 2 will come on the top? Do you have 100% confidence in telling the outcome of the die roll? Rolling the die? No. Right? There is some probability. 2 may come, 3 may come, 4 may come. You don't know. That process is called as stochastic. When you are tossing a coin, do you know that head will come 100% or tail will come? No. 50% of head, 50% chance of getting head, and 50% chance of getting tail. Got it what I'm telling? So you're not able to tell with 100% confidence that head will come or tail will come. This is called as random guess. This is called as stochastic process. Got it? Now, what is deterministic process? Deterministic process means you can do something with 100% confidence. Now, I give you the date of birth of a student. You can calculate his age with 100% accuracy. That is called as deterministic process. Now, I give you the date of joining of an employee into an organization. You can calculate his years of experience in that particular organization. With 100% confidence, you can do it. That is called as deterministic process. Okay. Now, here we are calling it as stochastic gradient descent. Why? Because you are randomly guessing a move to move towards the bottom of the hill. And you're descending to reach the minimum point. That is why it is called as stochastic gradient descent search. Now, this is similar to our current problem, least mean squares. Why? Because each time you're trying to take a move, each time the machine is trying to make a move from a current board state to a next board state and trying to make that move as best as possible in order to reduce the prediction error. It is called as minimizing the sum squared error. Got it? This is what I'm trying to tell. You're trying to adjust the weights. Each time the machine is trying to adjust the weights as it moves on to its goal of winning the game. Means adjusting the weights is nothing but it is trying to find the best move to its next legal board state. Got it? Can you tell me what is the time, students?
9:26, ma'am.
9:26. Again, we stopped at this position only. But is the concept very clear than previous class?
Yes, ma'am.
Okay, I'm very glad. Now let us move very slowly. I want you to be very comfortable with the fundamental topics so that later it will be easy for you to go. Your journey will be very smooth if you know the fundamental concepts very well. Okay, so I will take most time in making these concepts very clear to you. So let us again stop at the same point, not a problem. In the next class, I'll start again from this point. Now all the other concepts are very clear, so we can start right away from this particular concept in next class. Okay. Now before ending this session, again I have small questions for you. So whatever topics are covered on that only I'll ask the questions. Can anybody give example for stochastic and deterministic process? Later when you are reading some blogs and all, 1 second. When you're reading some blogs and all, when you come across this terminology, you should not be alarmed because they should not make you scary. All these are very simple terms. I'll just explain you with simple examples during the classes. Okay, tell me, what is example of stochastic and deterministic process?
Tossing a coin and dice because it is a random process.
Very good. Any other example can you give? That is what example I gave. Can any other example be given? Weather forecast is a stochastic process.
Yes, ma'am.
Guessing the performance of a student in exams is a stochastic process, highly stochastic for me, at least. Right?
Yes, ma'am.
Okay. Now, what is deterministic process? Given manufacture date of a product and expiry date of a product, you can understand for how much duration it can be used, right? With 100% confidence, you can calculate. That is a simple subtraction process, right? That is deterministic process. You can calculate something with 100% accuracy. Okay. Now, what is LMS? Somebody else I want you to answer. Apurva has answered sufficiently today. What is LMS?
Least mean
Square.
Least mean squares. Who is that? Two people on.
Honey, ma'am.
Umme
Ma'am.
and Harini.
Ma'am.
Okay, good. Least mean squares. Now, what has to be minimized in an LMS algorithm? Other students.
Sum of
Sum of
squares.
squared.
Sum of squared errors have to be minimized. What is that sum of squared errors? Can you give a more fashionable term for that? More appealing term for that? Means more catchy term I want. Sum of squared errors. Prediction. I'm giving you a clue.
False prediction.
False prediction. Yes. Prediction error. Gunashekar?
Yes, ma'am.
Yes. False prediction or prediction error. You are trying to minimize the prediction error. Now, what is W naught? Last
Error,
question.
ma'am.
Error. Who is this?
Paresh, ma'am.
Parish. It is error. Error associated in the prediction. Now that error has to be minimized. That is what we are calling it as sum of squared errors. This error occurs for every training example, right? For every training example, you're making a prediction. Now there is some error associated with those predictions. Now all that sum have to be minimized. Got it? Okay. How is your understanding in today's class? You're feeling it more comfortable than previous classes? You're refining your experience, learning experience? Students? Okay, let us meet in the next class to learn more better. Okay, bye.